Hello. In this video, I will introduce ordinary differential equations and introduce the two types of differential equations, ordinary differential equation and partial differential equation. I will explain how to determine if a differential equation is linear or nonlinear. And finally, I will do an example where I verify the given function is the general solution of the ordinary differential equation. So yeah, we are doing differential and ordinary differential equations. So yeah, intro to ordinary differential equation. So what is a differential equation? If you've seen the previous lecture that explains the differential equation, but I can review it. A differential equation is basically an equation containing the derivative of one or more dependent variables with respect to one or more independent variables, equations involving some unknown functions, and one or more of its derivatives. Okay, so in a differential equation, our solution is always going to be an equation, not like previously, like in your a solution is either a coordinate, but in differential equation, a solution is an equation. And there's a way you can check it to verify it is the solution. So, but first I want to talk about there are two types of differential equations. We have what's called ordinary differential equation. I'll abbreviate it as ODE. And we have partial differential equations. So in this lecture, I'm just going to go over ordinary differential equations. I mean, we're going to do problems related to ordinary differential equations. Okay, so an ODE, or ordinary differential equation, is a function containing only ordinary derivatives of one or more function with respect to a single variable, whereas a partial differential equation is an equation involving partial derivatives, which contains two or more independent variables. Okay, so an example of what an ordinary differential equation could look like would be like this: dy over dx minus y equals 2x, or y double prime plus 3y prime plus 6y equals e raised to the x. Okay, you know that this is like implicit. This is what form is that in? That is where it would be like prime notation, right? So this is implicit form, and this is prime notation. We'll go over more of that, but I want you to know that the order of a differential equation is the order of the highest derivative that appears in the equation. So the highest derivative doesn't mean the highest power, it just means the highest derivative. So if they're going to ask you what order is this differential equation, you just have to know it's the highest derivative, not power. So for example, if you are given this differential equation, we have d cubed over y over dx third raised to the second power. Okay, so this power doesn't really matter. It's this that's inside the parentheses that's really matters. So this is a third order. This one, even though this is raised to the 4, we don't really care about the power 4. We only care about the derivative. This is the second derivative, so this would be the second order. The same thing with here. This is raised to the third. We only care about what's inside the parentheses. This is the first derivative or first order. So this would be classified as the third order because this is the highest differential, the highest derivative, right? This is the highest derivative. It's not the highest power. Okay, so yeah, so if they ask you for order of the differential equation, it's the highest derivative. Okay, now let's talk about a little bit about linearity. How do you know if a differential equation is linear or not? Well, let's talk about the nth order of an ordinary differential equation. It's said to be linear if f is linear in the variables y, y prime, y double prime, or y to the n. So it's like coming back to here. None of these are linear because it has to be raised to the power of 1. So this is to the power of 2, so this is nonlinear. This one is raised to the power of 4. This is nonlinear. This is to the power of 3, nonlinear. Okay, but what if it was d3y over dx cubed raised to the first power? This would technically be linear because it's to the first power, right? Linear is always has to be in the first power, y equals mx plus b, right? The highest power has to be to the power of 1. So yeah, it's not the derivative power, it's the actual exponent. That's how I know it's linear. And then there's another uh, thing. It has to do with the coefficient, but right now, right now, there's actually two things that has to be linear. The power has to be to the highest power has to be to the power 1, and then something with the coefficient. But I'll explain that later. But right, so how do you know if you have a nonlinear ordinary differential equation? So the dependent variable y and all the derivatives are in the first degree. So if the it's not the derivative, it's not the power of the derivative, it's the power itself. If it's not 1, then it's not linear. And then this is also another important thing. The second coefficient, or the coefficient at most, depends on the most independent variable t or x. So okay, so what does that mean? So number 3 says the dependent variable y must be a linear function. So maybe if I give you an example. Okay, so let me show you an example. Let's show you, I will explain some examples. So here we have a differential equation column on the left, and we determine if it's linear or nonlinear. So on the left, you have dy dx plus 5y equals 0. Why is this linear? Well, let's look at our power. So dy dx, that is technically raised to the power of 1. They all have to be to the power of 1. This one is technically to the power of 1. Now this one, this can be anything. Yeah, this is fine. Wait. Yes, it can be equal to a constant. See how it says equal to 0? It could equal to a constant. So that's fine. Okay, so this works. Now you have to now look at the coefficient. So the coefficient cannot be it has to be in the derivative of the bottom. I mean, it has to be in the derivative of the coefficient cannot be the same letter as the numerator. That's what I meant. So if this had a y in it, which it does not, it would no longer be linear. It has to be it cannot be the coefficient cannot be in the derivative of the numerator. It could be if it was an x, that would work. If it was a z, that would work, right? As long as it's not the same derivative of the numerator. Right, this has no coefficient, has a 1. So as long as it's not a y, you're fine. The same thing here. This has a coefficient of 1. As long as it's not the same, it doesn't have the same letter on the top, so it doesn't have a y, so we're good. And this is good. So this is why it's linear. Okay. What about the second one? We have y double prime plus 5y prime minus y equals 3t squared. So why is this linear? Well, let's look at our power. So y double 2 apostrophe means like the second derivative, but it's still to the power of 1. So that's fine. And then let's look at the coefficient. This has a coefficient of 1. As long as it's not the same letter on the numerator, fine. So this is fine. This one is raised to the power of 1. So this is fine. And then this has a coefficient of 5. So as long as it's not the same power on the top, so as long as it's this 5, as long as this 5 does not have 5y, it's fine. The same thing here. This is power of 1. This has a coefficient of -1. As long as this coefficient isn't in the same wait. So as long as it is not As long as how do I say this? As long as it's not in the derivative of the, I keep forgetting. Is this the independent or dependent? I think this is the independent. As long as it's not, the coefficient is not the same, as long as the coefficient doesn't have a letter in respect to the independent variable or the whatever the letter on the top is, right? So yeah, it wouldn't have worked if it was y, right? That wouldn't work, but it's just a one, so it's fine. The same thing here. This is the power, this is all raised to the power of one, and this does not have a t, this coefficient does not have a t in it, right? It wouldn't work if it was like a 3t squared. So that's why it's linear. Let's look at this one. So why is this nonlinear? Well, so let's look at each term. So this one, y double prime, this is like second derivative. Yes, it's technically to the power of one. And yes, the coefficient does not have a letter y, right? So that works. What about this one? We have 5y, y prime. Well, did you know that 5y times y prime is the same thing as 5y times dy dx? So even though this is to the power of 1, the coefficient 5y has the same letters on the numerator, right? It's the same, it's in respect to the independent variable. So that's why yeah, so that's why this can be non-linear, because this coefficient 5y is the same, has the same letter on the top, or it's the same coefficient of the independent variable. So that's a big no. What about the second, this one? Y fourth is the same thing as fourth derivative. This is fine because it's still technically to the power of one. The coefficient is one. It doesn't have a y in it, so that's fine. What about this one? 5t y double prime. Yes, right? That's the same thing as 5t d squared dy over dx squared. So this this y prime is to the power of 1, so that makes it linear. And then the coefficient is 5t. As long as it's not in the this, it has a t in it, right? As long as it's not the same letter as the top, it doesn't have a y, so you're fine. The same thing with here. This is a constant, so that's fine. That's linear. Okay, what about this one? Why is this nonlinear? Let's look at each term, dy dx. This is to the power of 1. This has a coefficient 1, so that's fine. This one, cosine of y, because why is this not linear? Well, it's a trig. It's like cosine of y. There's no derivative, right? And also yeah, this just seems off. This is cosine of y, so there's no actual derivative. So that's why this is nonlinear. And basically, this is, I mean, if you graph cosine of y, that's a trig function, so that's why it's not linear. What about this one? Why is this nonlinear? So this one, this is fine, right? This is fine. This one is actually fine as well, right? Why? Because it's 5t and then dy dx. Because this is to the power of 1. This does not have a y in it, so that's why it's fine. Why this one, this is the reason why it's non-linear. What is square root of y? That's the same thing as y to the 1/2, right? And this has to be to the power of 1. So that's why it's a no. And let's look at the last one. We have 2xy. So why is this linear? Why is this fine? It's 2x, and then y prime is the same thing as dy dx. This is to the power of 1. The coefficient is 2x, and you're fine as long as it doesn't have a y, so that's why it's fine. This is fine, right? This is fine because it's negative 3y to the power of 1. So as long as it's to the power of 1, this has a coefficient negative 3, which does not have a y in it, so that's fine. And then 1 minus x, you know that's a linear. If you graph y equals 1 minus x, that's a linear function. So that's why it's linear. Okay, so our primary goal is to find the solution. So in a differential equation, our primary goal is to find the solution or solution of an ordinary differential equation. To do this, we need to understand the difference between implicit and explicit function. So the solution is valid on either an open interval or a closed interval. An explicit function is an equation. An explicit function is an equation written in terms of the independent variable, while an implicit function is written in terms of the dependent and independent variables. So an example of an explicit is when you have y on the left side, and then on the other side, it doesn't have y. So example is y equals 3x plus 5, y equals x squared plus 6x minus 8. That is an explicit example. So it's x equals a cosine parentheses and theta, and d equals rt. And implicit function is, so implicit is, when you did implicit differentiation, you would have like different letters all on both sides. So you have an x and a y equals 25. That's implicitly x, y, yeah. So basically implicit is when you have all letters, when you have different letters on both sides. Okay, notation. So you kind of know this already. Notation, you have f of x, y of x, y, etc. That's same thing as y. Derivative, you have Leibniz notation. You've seen this before, dy dx, d squared dy. This is like from implicit differentiation. This is second derivative. This is third derivative, right? You've seen this in implicit differentiation. And then you also have prime notation where you have those apostrophes. The first one means first derivative. Second apostrophe means second derivative. Third apostrophe means third derivative. And then when you go to the fourth and higher, they don't actually write four apostrophes. They just write the number 4. So this would be the fourth derivative. And then I don't think I've seen this before, dot notation. So 1 dot means first derivative, 2 dot means second, 3 dots mean third. Okay, so now you have some practice or idea of differential equation. So on these examples, A through uh, F, I want you to state the order of the differential equation. I don't want you to know, I don't care if it's linear or not, I just want the order. So on A, how do you know the order? Well, basically you look at the it's not the highest power, it's the highest power of the derivative. So dy dx is the first derivative, and this is to the power 1, or yeah, so this would be first order. The same thing with b, y prime equals 2x. It's not the exponent, it's the power. It's the highest power of the derivative, so y prime is the same thing as dy dx, right? This is to the power 1, so this is first order. Okay, C, we have a y double prime plus b y prime plus dy equals gt. So it's the highest derivative. That's what I meant, highest derivative. So this is not the highest, this is a constant, this is not a derivative, this is the derivative, this is the highest, this is second derivative, right? So that means it's second order. Okay, D. Okay, so this one, be careful with this one. It's the highest derivative. So look at this term. This is second derivative. Be careful with this one. This is first derivative, but it's raised to the third power. Remember, we don't care about the power, we care about the derivative power. So this is the first. This is not a derivative, this is not a derivative. So it's the highest derivative. So this is the highest derivative. So this is going to be second order. Okay, what about E? Uh, so this d cubed u over d squared dx, that is third derivative. One is a constant. This is second derivative, I believe. So it's the highest derivative. So this is the highest. So it's going to be third order. Oh yes, F. So we have which one is the highest derivative? Is it this one, this one, this one, this one, this one? Yeah. Yes. If you said this is the highest derivative, it is. So this would be classified as the fourth order. Okay, classification of linearity of an nth order ODE is said to be linear if it could be written as this. So it's kind of like the examples we done. Where did we do? It's kind of like these examples, or exactly like these examples. So what you have to do is, I'm gonna go down. But it could be in a form like this. As you can see, the derivative of the derivative has to be in the power of one. And then the coefficient, if it has a letter, it cannot be the same letter on the top. That's all it means. And then on the right, it could be a constant. So the dependent variable y and all its derivative are the first degree. So the dependent variable y and its derivative are in the first degree. That means you're looking for linearity in y only. Each coefficient of y must be in terms of x only or the independent variable. So it doesn't really have to be in terms of x as long as it's not the same letter on the top, or yeah, as long as it's not the same letter of the dependent variable or the same letter on the top, if that makes sense. So let's look at example. Give the order and state whether the differential is linear or nonlinear. So on A, we have dy over dx plus x squared y equals x. And we got to do two things, the order and state whether it's linear or not. So how do we determine the order? We look at the derivative, the highest derivative, the highest derivative, right? So dy is dx is a derivative, x squared y is not a derivative, x is not a derivative. So this is the derivative and its first derivative. So it would be first order. Now let's determine if it's linear. So let's look at each term. We have 1, 2, 3 terms we have to look at. So dy dx, this is to the power of 1, right? This derivative is to the power of 1. And then if you look, the coefficient has a 1. As long as it's not a y or the same letter on the numerator, you're fine. So this checks out. This one is fine. Y, this y has a power of 1. The coefficient is x squared, right? The coefficient is x squared. Now, you're probably thinking why this is a power of 2. It doesn't really matter as long as this is to the power of 1 and then this x, as long as this is not a letter of y. So this is fine. The same thing here, this is to the power of 1. This has a coefficient of 1. You're fine. So this all meets up, this satisfies. So this is a linear. So all of these meet all the conditions. So all these each term meets all those conditions. Okay, B, we have 1 over x, y double prime minus y to the third equals 3x. So let's look at the power, the order. So it's the highest derivative. So let's see, what is the highest derivative? I only have this. This is my highest derivative, and so that means it's second order because 2 apostrophe means second derivative, right? Is this linear or not? So let's look at each term. Uh, y double prime, that's fine. It's like the same thing as d square dy over dx squared, and it's to the power of 1. And you have a coefficient of 1 over x, right? As long as this does not have a y in it, that's fine. Uh, actually, no, this is not fine. Why is this not fine? Uh, this is not fine because this, oh, I know why. Okay, this is fine, but this one is not fine. Why? Because this is to the power of 3. It has to be to the power of 1, right? So the derivative and the just in general has to be power 1. So this y double prime is fine because this is second derivative to the power of 1. So that's why it's linear. This is not. This is to the power of 3. 3 is not linear. It has to be to the power of 1, so that's why it's nonlinear. Okay, see, let's look at the order. So what's the highest derivative? It is this one, and that is second derivative, so that would be second order. And then let's look at each term. There's 1, 2, 3, 4, 1, 2, 3, 4 terms. So this one, I think this is fine because this is to the power of 1 and has a coefficient 1. So yes, this one, I also believe it's fine because this is the just derivatives to the power of 1, and then this has a coefficient of x. That's fine, right? This is fine as long as the x is not a y. Now, what about this one? We have ln of y prime. So yeah, this is not good because this ln is not okay. So y prime is the same thing as dy dx to the power 1. That's fine. It's just that um ln is not linear. I think it would have worked if it was like ln of x times y prime. That'd be fine. But because ln is not linear, makes it nonlinear. Okay, D, we have, so let's look at our order. So highest derivative is y triple prime, so that's third derivative. So that would be third order. So our highest power is third order. Let's see, is everything in linear? So this one, let's look at the first term. I think this is fine because this is to the power of 1, and then the coefficient is 1 minus x, that's linear. What about this one? Yes, I believe this is fine because this is y double prime, and this is to the power of 1, and then the coefficient is negative 4x, which is also linear, so that's fine. What about 5 parentheses y, y, this is actually 5y. So this is linear, right? This is to the power of 1. The coefficient does not have a y in it. It's just 5, so that's linear. And what about cosine x equals cosine of x? Yes, why is this makes it linear is because the coefficient does not have an x in it, this is just a cosine, so that makes it linear. So this is why this is linear. Okay, let's move. What about there's two more. So let's look at E. This is fourth derivative. This is to the power of 1. Oh, so what would be the order? So the highest derivative is this one. This one, don't worry about. This is to the power of 5. That's not the. This is the second derivative, right? So this is the highest derivative, the fourth derivative. So this would be fourth order. And then you have an x squared here. So let's see if everything is linear. So this is fine. This is fine, right? This is to the power 1. This has a coefficient of x squared. As long as it's not doesn't have a y, it's linear. This one is not linear. Why? Because this is raised to the power of 5. This has to be, if it would have worked if this was to the power of 1, but it's not. It's to the power of 5, which is nonlinear. So that immediately makes it nonlinear. Okay. Okay. Go any more? Yes. Let's look at F. So we have T3 y to the fourth. This is y to the fourth derivative. And so what would be our high? I think this is our highest derivative, so it's going to be fourth order. And then let's check if everything is linear. So we have T3. So this is linear, right? This is to the power 1. The coefficient is T3, which doesn't have a y in it, so that's fine. This one is fine. This is first derivative to the power of 1. This has a coefficient of T3, negative T3, which does not have a y, so that's fine. This one is fine because this is to the power of 1. This is actually y to the power of 1, not y apostrophe. And this has a coefficient of 6. That's fine. So, and then this is a constant. That's fine as long. This could be a constant. So this would be linear. Okay, part G, we have d squared du dr squared plus, so let's look at the highest power. This is my highest derivative. That is my highest derivative, so it is second order. And is this linear? So let's check for each term if it's linear. So this is to the power 1. This has a coefficient 1. That's fine. This is to the power of 1. This has a coefficient 1. That's fine. This is y apostrophe, not y to the 1. So this is fine, right? This is fine. This is also, this could be y prime to the power of 1, and this has a coefficient 1. So that's fine. This one, this side does not make it linear because has a cosine. Cosine is not linear. So it's a trig function, so that makes it nonlinear. So that is why it's nonlinear. Okay, this one, what form is this? This is third derivative. So this would be, that's the highest power, so it would be third order. And is this linear or not? So this one is fine. This is to the power of 1. This has a coefficient 1. So linear. This one, see this power 2. This power 2 is not linear. This has to be power of 1. This can be whatever power, this could be whatever derivative, is that this power has to be to the 1. So that's why it makes it nonlinear. Uh, yeah, I'm gonna stop right here. I'm gonna do the second video on the other part on second video. So I will stop here. Thank you.